Okay, welcome to my presentation. My name is Kiszka, and I'm going to talk about the real-time topic you just heard out. My agenda, I'm going to give a bit about the why you're doing this, motivation scenarios behind it, give you an update on current real-time benchmark we are doing, and then we'll talk mostly about QEMU real-time improvements, because this is currently the big issues have to be solved, not that much in the kernel, and summarize the topic. So maybe you attended my talk last year. I was talking about KVM and embedded, and one of the point was why using KVM for embedded use scenarios was basically, usually you start small. You have a small hypervisor, just a few thousand lines of code. We heard this before this day. But then the requirements grow. And in the end, what you get is a hypervisor as big as something you get for for enterprise or desktop virtualization. So this is a good reason to think about if KVM is actually not a good use for this as well. And basically the same applies if you look at the real-time topic. So real-time right now is typically solved via various solutions, proprietary or open source, using some partitioning hypervisors. The advantage is that they have a high degree of temporal isolation simply because they allocate resources statically. So it makes things a lot easier to guarantee real-time this way. However, the flexibility, of course, suffers. The other thing is, if you're just not dealing with the real-time part, but also have to deal with some non-real-time general purpose part, you're not that much interested in getting into trouble with this part, just want to have it running, but usually you get a non-commodity setup this way. So the question is, if we are using a full virtualization in the sense of a full-blown hypervisor, of course, first of all, we have the disadvantage that real-time is not the goal of any of those hypervisors. Usually, they're not designed for it. And as they are providing a full set of features, they have a higher complexity naturally. So that makes establishing real-time for those hypervisors harder. On the other side, what you get is a much larger user base, at least for the commodity part. So you have a very good guest support, you have very good test coverage for those guests, and these are the parts you usually don't have to worry about. And you get a lot of more features this way, what your customers sooner or later will ask for. And actually, they have some common goal, these standard hypervisors, with what we want to achieve for real-time hypervisors. If you think of big machines, SMP scalability is also a topic for enterprise virtualization. So if you have big host machines, big guest machines, and their requirements are quite similar to real-time requirements. So there is some hope. So the typical setup of real-time guests there are basically three types of real-time guests. Either the classical RTOS, I don't want to mention any brand here, but you can imagine probably a few, which has been designed to run exclusively on some hardware and just doing real-time, nothing else. Or you have some AMP combination, so some real-time OS together with another real-time OS or together with a general purpose OS combined, which is running usually on a multi-core scenario on the physical hardware. Or you have a general purpose OS which also have to fulfill certain real-time requirements. For example, think of multimedia. Streaming videos, doing audio processing also has real-time requirements, softer ones, but anyway. So these guests, they need to interact with the outer world, and this is actually where the problem starts. Just enclosed and all virtualized is fine and easy to solve, but once you interact with the real world outside, you have those requirements to fulfill. So you have some interfaces you have to pass to the guest. Typically network interfaces, normal Ethernet or real-time Ethernet variants, or field buses. Think of the CAN bus in your automobile. Or you have some adapters for direct physical I/O, digital analog I/O card. So these interfaces either have to be passed through a classic approach, so you have one-to-one mapping from the physical interface to the guest, but you also often want to emulate them, either because you want to decouple your guest driver from the physical hardware you have on the host, simply because the guest driver is much older than your hardware on the host, or you want to solve some sharing issues. So you have less physical interfaces than you have guests, and then comes the point where you actually want to emulate the hardware. Or you even have a totally virtualized environment for testing purposes where you don't want to have any physical interface at all. So what is possible today if you look at KVM and QEMU? So I'm just running briefly through this. This is basically the setup we presented last year and even 2 years ago. So the setup is basically preempt.IT host and a preempt.IT guest, and comparing the numbers between both when running a timed user space task, both on the guest and on the host side. So what we do basically to enable this scenario is to patch QEMU so that it's able to prioritize the critical path, which means prioritizing the virtual CPU threads, the I/O thread, and deprioritizing everything else which we're not interested in for our critical path, which is this time task. And this is what you get still today, more or less. On this specific host, we measured about 30 microseconds worst case latency for the cyclic test running natively, versus around 110 microseconds when the same setups basically run inside the preempt.IT guest system. This is just to give you an impression about roughly the order of magnitude we have here. This test only ran for 3 hours. And yeah, if you run it longer, I bet you will also have a higher latency. So this is not totally absolute maximum, but it's a good feeling, but it's possible. Of course, you have to tune a lot. So you have to tune the guest to avoid certain I/O models, and you have to tune the host a bit to do the right prioritization. So that's mostly what has to be done, but anyway, not much patching actually on the code base.
So what latency are you measuring there? What is that latency you're measuring?
This is a time task latency. So a periodically programmed task is waking up and basically measuring itself the delay between the scheduled time and the actual woke up time. So we are relying here on the same clock source, TSC clock source, in this case x86. It was quite precisely measurable this way.
Excuse me, how did you measure in the guest?
As on the host with TSC, timestamp clock, which is accessible to both the guest and the host. This also, of course, involves disabling any scaling of the TSC and all the things, so that's what I mean about tuning the system. But it is a reliable measurement for this scenario. But this is a self-contained scenario, so let's look at a more interesting one. So this is a different guest system, an AMP guest system, which has a real-time part and a non-real-time part. And we are passing through, in this case, a network adapter, just to measure some round-trip times. So basically, it's the same host system, additional network adapter, and a virtual machine now with 2 virtual CPUs. 2 because the general purpose part of our guest system and the real-time part can actually already run on different physical CPUs when run natively. And we're exploiting this to run them on different virtual CPUs in the guest system. The advantage is that the real-time part has only a minimal footprint regarding its requirements on the devices, on the device model. So we only interact with the APIC and the I/O APIC and with the assigned device. That means no access to QEMU user space. Very nice. You will see why. And on that side, the general purpose part, this is a full-blown, or this is a requirement of a full-blown virtualization environment. Specifically, it requires to emulate VGA to boot up I/O. You may imagine what system I'm talking about. So we had measurement using ICMP, so basically a round-trip measurement against an external host, which is running in a real-time network stack. And we loaded the host system with various I/O and CPU load scenarios, and let the whole thing run for about 16 hours. And this is what we got. The worst case was around 300 microseconds The average about 150 microseconds. Too good to be true. Just before I left, the slides were already outdated because we had some peaks also beyond the 1 millisecond barrier. But we strongly assume that this is more a guest issue than a host issue. So the traces indicate that there's some delay. Probably our measurement setup was not that optimal using ICMP for this, although the guest was only dealing with the ICMP at this time. It may not be the best scenario for this. Anyway, it's also give you an impression what is possible in principle. If you do the same setup, not with a pass-through device, but with an emulated network adapter, this is what you get. 100 milliseconds, and well, I even measured seconds of latencies. Horrible, horrible. Although we prioritized the NIC IRQ, the soft IRQ of a host network stack, that was not the problem. The problem was actually QEMU. QEMU is still ruining any latency you want to get out of the system because of this big QEMU lock, QEMU mutex, global mutex. There's a lot of stuff done under this lock. Actually, is almost everything done under this lock. So we still have synchronous disk I/O, less these days. But even if you avoid it, there's network I/O done, which you're not interested for the critical path. Maybe there's the terminal I/O of the guest system.
How are you seeing 1 second latency for IO submit? So
this is a good question. I don't understand it as well. I just measured it once, and I measured actually that the syscall had a 1 second latency. I didn't follow this path any further, but
so Linux IO sucks. If you use it with something that doesn't support it, IO submit falls back to synchronous IO instead of failing.
Maybe this was the reason. Yeah.
So I think that's probably what you saw.
Might be the point, but it was a recent host kernel, and I think it should have worked. But anyway.
That's what it is. But
So are you using user space for IONet when you compare to QEMU, or are you using vHostNet?
We were using for the benchmark. We were using pass-through. So for other scenarios, I didn't actually compare Virtual or versus vhost regarding the latency issues. So basically,
the reason I ask is because when you use vHostNet, then you don't really have the QEMU mutex, right? Because then everything.
that's true. That's true. But
there's still scheduling, right? There's still the
right.
FD and the thread.
Yeah, this is part of the tuning you can do. You can try to avoid certain interaction. For example, if you're concerned about this terminal I/O, you can avoid that the guest uses the serial port and does all its interaction with a management environment via network, for example, and all these things. But sometimes you are not able to tune it this way because you don't have the guest drivers prepared for it. Or the guest simply assumes there is a serial port and is using it, for example. The point is actually there's too much stuff there. Also, if you're dealing with a graphical guest, you have huge latencies, for example, to synchronizing the graphic RAM for regular updates. So I measured above 10 milliseconds, for example, just for synchronizing the dirty bitmap blocks. And there's probably much more. In short, if you're concerned about real-time, the global mutex must be avoided for any real-time relevant code path in QEMU. So what can be done? This is our roadmap we are trying to follow right now. I will go through some parts rather quickly, but there are a lot of topics to be addressed. Some of them are more easier, some are more harder. Let's start with the easier ones. If you want to decouple the various I/O models in QEMU, you first of all have to decouple the CPU state. So basically, this is actually already done right now, more or less informally, so that every vCPU owns its own vCPU state, and only the vCPU thread or context touches it. This should be established formally. So that basically there is no write access to the vCPU state from a different context other than the vCPU itself, unless the system is stopped, of course. Also, CPU, I think it's single env, this famous global pointer still exists and has some use cases, unfortunately. We have to convert it to a per thread variable. I think we did it in the past with QEMU KVM, but then convert it back. As long as this pointer exists and has some meaning, it has now to become a per CPU variable for this scenario. Next step. If we take an I/O exit from the guest, it wants to issue some I/O request, we have to first of all identify what device is addressed. So what we have to do is to walk the memory map, obtain the handler behind this, the device reference, and invoke the handler and let the device model run, basically. So across this path, we need some kind of synchronization between changing of the memory map, of course, and here in this case, accessing it.
Just use RCU there.
Yeah, I was just going to say that's the
RCU, but I would say it's even that is. I think we could do simpler. Just simply what the KVM tool in this case is doing already. Simply either stop the machine if you modify it, or leave it just running. You don't need to worry about any RCU specific extension in this case. If you just only modify the memory map when the system is stopped and no CPU is running or using it any reference right now, if you know all vCPU and all other I/O threads are in a well-defined state, you can modify it and yeah, you're done basically.
If you use RCU, you say you solve half of the problem also for migration.
Yeah, the question is actually, well, RCU means that you also need to import all the environment around it. User space RCU is not that trivial. I haven't actually used it before, but I found that there's a few, maybe also portability issues regarding Windows or so. I'm not sure. I think a current user space RCU is based on signals, so.
How does stopping the machine help? Suppose you stop the machine while...
You bring all vCPU and I/O thread in a well-defined state where you know that they're not no longer holding any reference to the things that you want to modify. That's basically the point.
Okay, so you let them complete any IO transactions that are in progress. Okay.
It's a big hammer approach right now, but I think it's sufficient for this particular use case. If you have other use cases for RCU, I'm all fine for it, no problem. But I think for this case, it's enough just to do this big hammer approach. Another topic is coalesce MIO.
Well, the other thing you can do is you can differentiate between mappings that change and mappings that don't change, right? Because there actually are very few mappings that ever change.
Yeah, but already if you look at the PCI device, the PCI device can be hot plugged or can be remapped. Just to make it simple, you'd have nothing one. Sorry?
You can have a memory and
You've been saying that for 5 years.
Yeah.
You can. Well, eventually it will be true, but you can't just pretend it's not the never exists.
But it's definitely not a hot path.
Yeah, that's true. Coalesce MIO, another topic. Important right now, specifically for VGA, or graphic emulation in general. Unfortunately, right now, a contention point because we only have one MIO request ring per virtual machine. So you don't need synchronization between readers and writers. This is lockless, but you need synchronization between different readers. So different vCPUs trying to replay the coalesce MIO requests. So they are currently synchronizing via the global mutex. This is, of course, a no-go, as we know. As a short-term solution, we can simply skip this flushing unless we are going to process a device which relies on coalesce MIO. For the E1000 would mean to disable it for now. But the long-term solution is actually to have multiple rings or multiple buffers for this. And there was some discussion also recently about socket-based I/O event FD, which might provide such a mechanism.
You can have weight-free data structure. Weight-free just for the queuing. The enqueuing can still be locking, but the queuing is weight-free, or vice versa. I mean, just at this point.
Yeah. Okay, we heard about a bit the IQ forwarding or IQ handling problem in the context of device pass-through. Basically, what we are facing here is the same issue. We don't want to walk through all the devices for the common case, for the fast pass, because it would require synchronizing a lot of critical sections there. We can't do this already, as we know, if sync and source are in the kernel. Or we could do it, but we don't want to. On the other hand, the suggestion was made this early morning by Alex. I don't like it that much, actually, because I think we need an even more generic approach. Anything which mentions PCI or mentions something which is x86 related is too specific already. We basically need an approach which allows us to discover the current IRQ path so that you can establish a fast path between source and sink. And you need some notification mechanism that if something changes in the path, that the path is rediscovered. And you also need some polling mechanism. So if some intermediate step, some router step, wants to know or wants to read out the current state of the IRQ level pass through, it can basically pull back the chain on demand. But for the fast pass, we don't want to involve any of the intermediate routers. That's the whole point. That was the simple part. Now come the harder parts. To do really concurrent device models, we first of all need mandatory, whatever we do, separate context for handling host-originated events. So everything which comes from the host towards the guest needs to be handled separately as far as possible to allow event prioritization. We don't want all host events to be processed by the same or at the same priority level when doing real-time usually. We also want to do it probably in parallel. It's also interesting for other use cases in real time. Maybe we leave the I/O thread running, probably for intermediate time anyway, as the pool for any best effort work. But anything which is critical for real time should have its own context. And then we basically are exploring two variants right now, but I want to go a bit in detail right now. So one approach is the classic one you can think of probably first is, well, a lock for every device. That means this lock protects any atomic section of the device model while processing requests issued by the guest or while processing events issued by the host. And this lock could be taken then either over the vCPU context or over any of those I/O thread contexts. That means we also need separate I/O threads, as I said, so to process those host-originated events. Either they could work on a per device granularity, or maybe also pooled again to make management a bit simpler, grouping certain devices. The downside of this approach, if you think in the details, this is a corner case actually, but we want to remain correct also for the corner cases. Think of an I/O request issued by the guest CPU. It addresses a certain device, and the device, as a reaction in the same context, issues another I/O request, a DMA request, backward. In this case, not targeting the RAM, which would be the simple case, but another device. It's possible. So you end up into a loop if you're unlucky. You end up with taking locks in a nested way, maybe even lock recursion and deadlocks are theoretically possible. So the question is simply how to resolve this in a well-structured way. And if you think into details, it's not that easy, because you can also take it another way around regarding this lock ordering. Sometimes you can resolve it depending on the device model, because you don't have to hold the lock of the device issuing the DMA request while issuing this request. But sometimes you may be not able to do this. So the idea we had, we are trying to explore is to use a server thread approach. So we have a thread, at least one thread per device, which runs all the jobs the device have to do, which are heavy weighted. Either any host triggered work, but also complex guest triggered work. So certain guest requests, I/O requests, are now forwarded to the server thread and processed there. That means if you have a write request, this can either be a synchronous request to the server thread, or if you don't have to wait on some reaction, you can make it also asynchronous. Reads, of course, if you want to expect some data read from the device, and you of course have to wait in the vCPU context on the result. On the other hand, you don't want to handle all the I/O requests this way, because it's of course a heavy weighted way, involves context switches and all the things. The trivial ones should still be possible to be processed over the vCPU context, which basically means if you just want to read some device register or set some device register which have no other side effects, this should be done completely lockless, completely asynchronous, at least in theory for some devices. So this makes actually this model quite attractive. If it works out for the majority of devices, I think it would be quite a nice one. On the other hand, The downsides here are that you need to think about ordering of state changes in your device models. This may become complex by if you think of more complex devices. Maybe you also have to introduce some atomics or barriers to make this ordering work. So this is something we need to explore right now. So we're right now trying to implement what I sketched. The first steps are already done and are still working. We are currently focusing, as I said, on this variant B, so the server thread model. See how far it will take us. The goal is to get at least the E1000 device model decoupled from the rest, and then do the measurement again that we saw earlier, using, of course, KVM with in-kernel Yaku chips, so nothing user space. So this current focus is set on QEMU, not that much on the kernel side, because there are still much lower latencies to hunt. So because of the time, I'm skipping over this. Just in short, if you think about using the glibc's condition variables and mutexes for real-time purposes, be warned that the priority inheritance mutexes and condition variables are broken together in glibc. This is a normal approach to take if you prioritize some threads and you run into these problems. Unfortunately, glibc folks are not interested in this problem right now, so we have to work around it. But yeah, that's an off topic actually, but yeah. So there are many benefits actually in using KVM as a real-time hypervisor, because you get a lot of features in addition to compared to partitioned hypervisors. And you get the matrix support for the standard guests you want to handle this way. Still, there are some restrictions regarding real-time. It works mostly fine if you leave QEMU for the hot path out of the picture. But once you enter user space, you either have to tune a lot the guest system that certain device models are avoided, otherwise you run into huge latencies, really, really huge latencies. And this is where we're currently focusing. We try to improve the situation, to parallelize the QEMU device models. So as I said, the next goal is to run emulated real-time networking under RT conditions and basically get below 1 millisecond as a round-trip latency. We think that the outcome of this work will also provide some benefits for general purpose KVM scenarios when it comes to SMP scalability on large boxes. So there should be some benefits for everyone here. Thank you for your attention, and yeah, any questions?